Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Lecture 6, Week 1 of Dynamic Atomic Force Microscopy Methods. In the last class, we had talked about a brief review of tip-sample interaction force models, and we had talked about the fact that when a tip is oscillating near the surface, that you can decompose the interaction forces between the tip and the sample as an additive sum of a conservative interaction and a non-conservative or a dissipative interaction. And the conservative action, or part of the tip-sample interaction, can be regarded as being only a function of the tip-sample gap without any dependence on which direction the tip is moving in or the velocity that it's moving in. All that matters to determine the value of the conservative interaction force is just the gap between the tip and the sample. The other component is the dissipative interaction, which arises from effectively many relaxation processes, many hysteretic phenomena that occur between the tip and the sample, which include, for example, the formation and breakage of capillary necks, formation and breakage of adhesive bonds between the tip and the surface, and due to the generation of phonons, the generation of heat, friction. All these are different anelastic or dissipative phenomena that ensure that the force encountered while going towards the sample is different from when it's coming out during an oscillation cycle. And so this additive decomposition is a nice mathematical way to keep track of both these components. What we're going to do today is to ask ourselves a question: what happens if we get our point force or point mass model for the cantilever and bring it close to the sample surface? We're going to break this discussion up into two parts. In today's lecture, we're going to look at the transient vibrations without any external forcing, without any lithium piezo excitation or magnetic excitation. Basically what we're going to do is bring this point mass model close to the sample and ask ourselves the question, how does the tip oscillate when you ping it or disturb it due to the influence of the tip-sample interaction forces? And on the top left is shown notations that we're going to be using for this discussion. The key thing to keep in mind is that D is the instantaneous tip-sample gap, Z is the separation between the surface and the tip when the tip is not deflected. And you can change Z. The way to remember this is that you can change Z by changing the sample position, by moving the sample up and down, or moving the base of the cantilever up and down. Q is the displacement of the tip from its undeflected position. The way we have set it up is positive deflection upwards, Q is deflection upwards, negative Q is deflection downwards towards the sample. If we go ahead and do a free body diagram for the mass, as shown in the bottom left for the point mass, it's easy to derive the equations of motion as shown in 1. The difference between this equation of motion and the transient equation of motion that we studied a few lectures ago is the fact that now we have right-hand side, which is the tip-sample interaction force, which does depend on tip displacement Q in a nonlinear fashion. As you know, and as we have discussed, the interaction force is not going to be a linear straight function of Q, but rather it can change its slopes and bend and twist in interesting nonlinear ways. So this is also what's called an autonomous equation because we don't have any excitation included. We don't have any magnetic forcing or lithium-piezo excitation. So there's no explicit time-dependent term that occurs here. So we call it an autonomous differential equation. So even if it's autonomous, this differential equation is not easy to solve. So we're going to have to try and understand what this equation tells us about the physics of the problem using some simple approximations such as linearization that we're going to talk about soon. So the first step in trying to understand what's the physics of what happens when this oscillator is brought close to the surface is to break up the solution into two parts. So Q is going to have two components. One is going to be a static component, Q star, and then there's going to be a fluctuating component Q tilde. The static component Q star is effectively the solution to the static equation of motion, which is the equation of motion when there are no time-dependent terms. So if you set all the time derivatives, ddt's, the dots to 0, the equation that remains is shown here is equation 3. Equation 3 is written in terms of Q star, and this is the equilibrium equation, and you can solve for Q star, which is the deflection of the probe tip, as a function of z, which is, the separation, which can be controlled by changing the sample position or the base of the cantilever. So in order to move ahead, what we do is to take this, this decomposition between the static and dynamic parts in equation 2 and plug it into equation 1. And we find we reach equation 4. And if we make a further approximation, which is described in the appendix, this is called the linearization approximation, where we assume that the tip displacement or the dynamic tip oscillations, the Q tildes, are extremely small compared to the tip sample gap D star, the equilibrium tip sample gap D star. So, as we have discussed in part 1 of the class, the tip sample gap where you start experiencing van der Waals forces could be of the order of a nanometer. So that's the D at which you start experiencing van der Waals forces. So in order for the linearization assumption to hold good, the Q tildes, the dynamic fluctuations need to be much smaller than the gaps D star. So perhaps of the order of an angstrom or even lesser. That's the oscillation amplitudes for which this approximation would be valid. And nonetheless, it gives us a lot of insight into the physics, and we'll proceed with this approximation. So when you go through the derivation, which is given in a little more detail in the appendix, you reach the transient equation of motion, equation 5, which tells you how Q tilde behaves due to the presence of the interaction forces. What's really interesting is the presence of the interaction forces can be clumped together in 2 terms. One term accompanies the Q tilde itself. Another term multiplies Q tilde dot, or the tip sample velocity, or the tip velocity. The term that multiplies Q tilde is basically the square of the natural frequency, and so, as we'll discuss pretty soon, one effect of the tip sample interaction force is going to be to change the natural frequency of the probe. The second term, which multiplies Q tilde dot, Q tilde dot, the velocity of the tip, is connected to the Q factor. So that means that even the quality factor, or the effective quality factor, is going to change because of the tip sample interaction forces. The last equation on the bottom of the slide is repeating the static, the equation that governs the static solution. So what we're going to do now is to first just review what the typical static solution is like, and then we'll move on to the transient equation. The static equation given at the bottom of this slide is in terms of Q star, but if you remember that Z plus Q equals D, we can rewrite this static equation in terms of D, as shown on the following slide. So on the very top here, I've got the equation written in terms of D star, and let me go ahead and go to the board and try to review briefly what solutions one might get out of this equation. So the equation we're trying to solve is K D minus Z equaling FTS as a function of D. So any solution to this it's not a differential equation. Any solution to this equation will satisfy the equilibrium requirements and balance the forces. So what we're going to try and do in this thought example is going to be to change the Z, which is the separation between the cantilever and the sample, and try to figure out the value of D star that satisfies this equality. And in order for a value of D to satisfy this equality, we can graphically look at it as the intersection of 2 graphs, right? One graph is that of the tip sample interaction force as a function of d, which is drawn here for a canonical situation. The other is simply the graph of k d minus z. So, for example, if I were to pick a value of z, like so, this would graph as a straight line whose slope would be k. The intersection of these two graphs occurs here, and that value of d at which these two graphs intersect is going to be the static gap d star, and the amount that the cantilever tip had to deflect down by would be given by q star out here. So what we'll do now is to step down in z and approach the sample by reducing z and try to see how this tip sample deflection, or the tip deflection q star, changes as you change the separation between the cantilever and the sample. So what I've shown in this graph on the left is precisely this intersection between the straight line and the tip sample interaction force curve. And if you go to the point labeled 2, you precisely see what I sketched on the board right now, which shows that the intersection occurs at a certain value of q star. As the tip sample separation is reduced and you get to point 3, the straight line intersects with the tip sample interaction force curve at 2 locations at 3 and 3 prime, which means that the tip is in equilibrium with the tip sample interaction forces at 2 different locations of the gap d star, or of tip sample deflection, or tip deflection q star. And so what ends up happening as you move from 1 to 2 to 3 to 3 prime is the following. The cantilever comes in, the q star becomes more negative, it dips down under the action of attractive forces, and then when you go from 3 to 3 prime, there's a sudden decrease in q star. Q star goes to even more negative values. It has to bend down a lot more, and then it gets and it touches the sample. Beyond that, when you reach point 4, the base of the cantilever is going down, or the sample is moving up. And then when you reach point 5, the tip deflection has actually become positive relative to the base. And that's point 5. When you go from point 5 back to 4, back to 3, at 3, you don't have a continuous possibility of a jump from 3 prime to 3. So from 3 prime, you just go to 6. Point 6. At point 6 now you have the simultaneous existence of another position of the tip where the forces are going to be balanced, that is 6 prime. So then you go from 6 to 6 prime, and the tip snaps out of the sample, and you go back to 1. What's shown on the right hand side is the same graph, however, where the solutions are shown in terms of q star, which is the static deflection of the tip, as a function of separation z. We find that when you're far away, z is far away, you're at 1. When you come closer, the q star becomes more negative due to the attractive forces. At point 3, it suffers a jump and becomes even more negative as it snaps down below. And then as you keep pressing down, or the sample moves up, q star becomes positive, the tip deflection becomes positive. When you move back out, you get to point 6, where the tip deflection is very negative, and suddenly it releases and then goes to 6 prime, where the tip deflection becomes again nearly 0, and finally at 1 you're well separated from the sample. So this is the static solution part of the problem. Now what we're going to study is what happens when at a certain z the tip is bent down by q star. If you ping it, how would it oscillate? And that is described by the transient probe motion that we derived a couple of slides ago. The key thing to note is that if you look at all the terms multiplying q tilde, they must equate to the square of the natural frequency. So we see that we can define a new natural frequency, which is omega naught prime, and Omega naught prime in terms of omega naught is shown on the left in this equation. We find that omega naught prime squared is given in terms of omega naught squared, and a whole term in parentheses which includes in it the gradient of the tip sample interaction forces. Now traditionally this gradient is written with includes the negative term as I've shown here, and the whole thing is together with the negative term is called K sub Ts. On the equation on the right hand side, we look at the term that multiplies the Q tilde dot, and we're able to derive an expression for the new effective Q factor Q prime as shown by this equation. Again, we find that there is an additional term for the tip sample dissipative forces that comes in, and that term, which is partial F partial tip velocity, evaluated at the equilibrium position or the static position of the tip, is called the tip sample viscous dashpot. So just like we had a dashpot for describing the damping or the dissipation due to surrounding viscous fluid, you can think about, for very small oscillation amplitudes, you can think about a viscous dashpot reflecting the energy loss that occurs due to all these anelastic processes that I mentioned to you at the start of this lecture. Again, traditionally we put a negative sign in front of the quantity, and so CTS is this whole term with the negative sign included in it. And so the bottom line here is that as you bring this probe close to the sample, there's going to be a static deflection, and you can ping it and study the transient response by looking at the natural frequency and how it decays, which is what the Q factor is about. We find that the tip sample interaction forces actually influence both the natural frequency on one hand, as well as the damping, effective damping through the Q factor. So out in equation 6, I have rewritten these expressions for the modified natural frequency and the modified Q factor. And traditionally, KTS is written in a way such that when described as the gradient of the tip sample interaction forces, when this quantity KTS is negative, we have what's called an attractive force gradient. To explain this better, if you look at the graph on the top left, I've got a canonical tip sample interaction force profile. If we choose the value, the green dot where I've shown where it is, and if one looks at the slope of it, it's very clear that the quantity KTS must in fact be negative for that particular position. So we call that an attractive force gradient because KTS must be negative. On the other hand, if Z is reduced quite a lot, and one goes into what's called the repulsive force gradient, where the slope changes as shown, in that case KTS would be positive, and you would get a repulsive force gradient. It is instructive to try and get a physical feel for what an attractive and repulsive force gradient mean. So I've sketched out at the bottom here 2 examples from daily life about what a positive and negative repulsive gradient would be, or a negative gradient would be. A positive tip sample interaction gradient would be a repulsive gradient, which can be mimicked by a spring. So if you've got a slinky or a spring and you're pressing down on it, it would repulse indentation, and the spring constant you get from it would be a positive K sub Ts. Now on the other hand, if you're holding a horseshoe magnet, for example, and over an iron surface, as you move it closer to the sample, the attractive magnetic forces would increase. We would denote that as a negative value of KTS, suggesting that the attractive forces keep increasing as you come closer to the sample. And as a result of this, what equation 6 really tells us is that when you have a repulsive interaction force gradient, you end up getting a natural frequency that increases relative to omega naught. When you have an attractive tip sample interaction force gradient, the natural frequency decreases, the oscillator slows down in comparison to what it was far from the sample. When you look at the second part of equation 6, which is for the Q effective, that can be described in terms of C sub Ts, which is this tip sample viscous dashpot, or dissipation, if you will. We find that CTS is typically always greater than 0. It doesn't change sign usually, as does K sub TS, but we typically find that CTS remains positive, which means that the Q prime, the effective Q factor, keeps decreasing as you bring the probe closer to the sample. So these are the two main effects I wanted to talk to you about, is what we expect to see when you bring a oscillator close to the sample and examine its natural frequency, that its natural frequency should first start decreasing due to attractive interactions, and then it should start increasing due to repulsive force gradients as you come even closer to the sample. On the other hand, the effective quality factor as you approach the sample should just keep decreasing, reflecting overall increase in dissipation. Thank you. See you next time.